So welcome to the Honors Tutorial Center. Our topic for today would be the chemical energetics and rates of reaction. So an introduction to chemical energetics. What are or what is this chemical energetics? All chemical changes are accompanied by the absorption or the release of heat. And this heat is known as your energy. Okay? Then the intimate connection between matter and energy has been a source of wonder and speculation from the most primitive times. So how does the matter and energy interact with each other? Because we already know that matter is anything that occupies space and it has mass, right? And then energy, when we say energy, you cannot you cannot create energy, nor you cannot destroy it, but we can actually convert it from one form to its other form. Okay? Just like the most or the very most common energy. If I'm going to ask you, can you give me the two most common energy on earth? What are the two most common energy that we have? The two most common energy on earth, we have the potential and the kinetic energy. Okay? That if you're going to define what is potential energy, the common definition is energy at rest. But while the kinetic energy is the opposite, it is now the energy in motion. And later on, we're going to discuss it. We're going to discuss it in a full detail. What is a potential energy? What is the kinetic energy? Okay, but in chemical energetics, we will begin the study of thermodynamics, which treats the energetic aspects of change in general, and we will finally apply this specifically to chemical changes. Okay? So there is one branch of physics that is merely or directly involved in chemical energetics, and this is now the thermodynamics. Energy changes during chemical reaction. Okay? So there would be
Okay.
a change in energy if ever there would be a reaction in your chemical. Now, obviously, a lot of chemical reactions give out energy as heat. So, in short, energy is being released. Example of this one, we have the combustion. There is now a release of heat. Okay, it doesn't absorb heat or it doesn't absorb energy, but it will release. Getting
Ah,
heat by burning a fuel is a simple example, but you will probably have come across lots of others in the laboratory if you have a laboratory activities. Okay, another example, if you're going to if you're going to light a match, okay? Do you know a match, a matchbox? Okay, if you're
yes.
going to light a match, then you are releasing heat. You are releasing energy, okay? By a chemical reaction in the match and in the box. Another example. Do you see this one? Yes, okay. It is now a lighter. It contains the sprinkle, and it contains also if a gas here or a fuel. If I'm going to switch on this one, you can see flame, right? Or a fire. There is now a conversion, or there is now a chemical reaction between the starter and the fuel. The fuel is being burned, so there would be a chemical reaction. The fire that you can see is now the energy or the heat being released in the atmosphere. So that is now the chemical, the first explanation. Second, other reaction or reactions need a continuous supply of heat to make them work. Example is splitting calcium carbonate into calcium oxide and carbon dioxide. It's a simple example of this one. Any chemical reaction will involve breaking some bonds and making new ones. And what are these bonds that is being broken down? Can you give me the two bonds? You call it as the covalent and the ionic bonds, right? So the ionic and the covalent bonds are the ones being broken down and making a new ones. So it's either if the covalent bonds will break down, it will make either another covalent or a ionic bond. Okay? It depends on the reactants and the products. If the reactant is two nonmetals, then it is ionic. If it is nonmetals and metal, then it is covalent. That's all. Okay? Third and last, energy is needed to break bonds and is given out when the new bonds are formed. Meaning, if if a chemical reaction needs to break the bonds between two elements, then energy is being absorbed. Now, if this energy being absorbed breaks the bond and it will now make a new one, then the energy being absorbed is now given off or released in the atmosphere. That's all. If you need to break the bonds between two elements or two compounds, that compound or that element will absorb energy in order for them to break the bonds. But if the bonds is now being broken, and it will now make a new bonds between the newly formed compound or elements, then the energy that is absorbed is now being released. So here's a very specific example that you can relate. Okay. In the morning, when we wake up, so we need to take our breakfast, right? So we're going to eat, drink milk, drink juice, drink tea, or drink a coffee in order for us to have energy. Okay? So now energy is being released, being absorbed by our body through the food that we take. Then after we eat our food, our breakfast, we will now go to me, I will go to work. You will go to your school, right? So from our house to workplace or school, we are now releasing energy. Okay? We are now releasing the energy that we take from our breakfast. Then after we release this energy, you can feel it that you don't have any energy anymore. So during lunchtime, you're going to refuel again. Then take your lunch for the afternoon activity. Okay? So from there, you're going to release also or again the energy that you take or absorb during lunchtime. It is now the same as this one. Okay? As the energy needed to break bonds and it will now give out when a new bonds are formed. So that's the main function of energy being absorbed and energy being released. I have here a simple energy diagrams. The first is that a reaction in which energy or heat energy is giving off or it is being released. You call it as exothermic. So it is being released. But if it is energy or heat energy being absorbed, you call it as endothermic. I'm going to give you a hint. Okay? If you are identifying if it is exo or endothermic. Okay? From the word itself, exothermic. Thermic means heat energy. Exo means to release. Okay? Energy is being released. That's why exo. If endothermic, thermic means heat energy. Endo means absorb, to take in heat energy. Get it? So we have here an example of exothermic. There you have it. So this is now the energy level, and this is now the progress of the reaction. This is now the product, and this is your reactant. Now, in the example of exothermic, meaning there is now a heat release or energy being released from your reactant and the product, heat is being released. This is now the diagram. Notice that in an exothermic change, the products have a lower energy than the reactant. The energy that the system loses is given out as heat to the surroundings warm up. Okay. In exothermic, the energy of the product is lower as compared to the energy of your reactant. Why? Because there is now a loss of energy or energy is being released to the surroundings. That's the reason why. For example, if your reactant has 5 joules of energy and your product have a 3 joules of energy, meaning it is exothermic because the 2 joules of energy is now being released in the environment. Okay? That is now the example and explanation of exothermic. To summarize it, reactant has a higher energy compared to the product because energy of the reactant is now equivalent to the energy of the product plus the energy being released. Next, we have the endothermic change. Here you have it. Okay? It is now the opposite way of your exo. In here, in the reactant, is that energy of the reactant plus the energy being absorbed is now be equivalent to the product's energy, meaning the heat energy is being absorbed in endothermic. Now, this time the products have a higher energy than the reactant. The system absorbs this extra energy as heat from the surroundings because you do need heat in order for a chemical reaction, right? Now, we will express exothermic and endothermic changes in numbers so that you have an idea on the absorption and releasing of energy in the environment. In here, first, we have the exothermic reaction showing the amount of heat evolved. Exothermic, meaning there is now a release of heat, right? So, carbon plus oxygen, you have carbon dioxide. And the change, this is change, okay? The change in heat would be equivalent to negative 394 kilojoules mole negative 1. Okay? So what does this mean? This shows that 394 kilojoules of heat energy are evolved when equation quantities of carbon and oxygen combine to give carbon dioxide. The mole raised to negative 1 per mole refers to the whole equation in mole quantities. If heat is being given off or it is being released, therefore your energy should be negative, or the change in your heat is negative. Okay? That is always negative. But if it is in Indo, it is positive because you gain energy, you absorb energy. So it is positive. For example, you do have your money in your pocket is 20 pesos. If you give that 20 pesos to your brother gain a positive 20 pesos, right? But you gain a negative 20 pesos because you release, you give off. Do you get it? It is just the same principle, absorbing and giving off. Now, if you have a sort of question, sir, how did you arrive to a 394 kilojoules as the change in energy or change in heat energy of carbon dioxide from carbon and oxygen? Okay, so that is the question. How do I derive from this change in energy or change in heat? The answer is there is a table showing the energy of each element. Okay, so it is constant. So if ever I gave you or I'm going to give you an exercise regarding this one, just look for the table itself because the value of the energy per element is already there. Actually, there is a formula of this exothermic and endothermic, but don't get so excited because we're going to reach it. But first, we're going to talk about the formula of your potential and your kinetic energy first, before proceeding with the formula of your exothermic and endothermic. Then after we discuss the four formulas, we will proceed to the thermodynamics in order for you to relate all the topics in chemical energetics and rate of reaction. So for now, just relax. Okay? In here, there is a question. How do you know that heat is evolved? That is shown by the negative sign in here. That's the one that I am talking about a while ago. Now, you always think of the energy change during a reaction from the point of view of the reactants. So the reactants, in my example a while ago, is the carbon and oxygen. So those two are the reactants. Have lost energy during the reaction to form a carbon dioxide. The energy which is causing the surroundings to get hotter. That's the reason why our environment is sometimes hotter than the usual temperature because there is too much carbon dioxide in our surrounding. Have you noticed if you're going to get a plastic bag, then put it in your mouth and nose like this, then try to blow it. Blow and blow until the plastic bags become a balloon. You can feel the air inside your plastic bag is hot, right? It is hot because it contains carbon dioxide. Now, if you're going to touch a water from a fish pan, if you're going to submerge your hand, okay, in that fish pan, you will notice that the water is cold, or even in a aquarium. Okay, in aquarium, just submerge your hands up to here. Okay, up to here. You can feel that the water in your aquarium is cold as compared to the environment that you have. That is due to the presence of the oxygen. Okay? there is a higher level or concentration of oxygen in that aquarium as compared to the environment that you have. Okay, now you know. Oh, this water is cold. There's lots of oxygen. Okay, now we will talk about the endothermic change. Your reactant is calcium carbonate, and your products are calcium oxide and carbon dioxide. And the change in heat energy is a positive 178 kilojoules, meaning there is now an absorption of energy or heat energy. Okay, so there is now an absorption of energy. That's why the change in your heat is now equivalent to positive, this is positive 178. Now, you can tell that the energy is being absorbed because of the plus sign, the positive side. In here, this is now the diagram. So you have here your reactant and your product. The energy of the product is much higher as compared to the energy of your reactant. So whenever you write values for any energy change, you must always write a plus or a minus sign in front of it in order for us, in order for a teacher or your classmate to identify whether it is a exothermic or an endothermic change. Okay? So now, let's talk about energy. So let's take it step by step. So what is energy? So energy is one of the most fundamental and universal concepts of physical science, but not that is remarkably different to define in a way that is meaningful to most people, meaning the fundamental and universal concepts of physical science. If we're talking about physical science, we are now talking about physics and chemistry. Okay? So energy cannot be created or destroyed, but you can convert it from one form to the other form. So you cannot destroy it. You cannot create it. For example, sir, I don't have energy. I cannot say that I will create an energy for you. No. You cannot create it nor destroy it. And this energy is the fundamental law of nature, more properly known as conservation of energy. Are you familiar with the law of conservation of energy? So it's familiar to anyone who has studied science under its more formal name as the first law of thermodynamics. So the first law of thermodynamics is known as the conservation of energy, and it governs all aspects of energy in science and engineering applications. Its special importance in chemistry arises from the fact that virtually all chemical reactions are accompanied by the uptake or release of energy. Chemistry arises from the fact that virtually all chemical reactions. That's the reason why a while ago you have noticed that, sir, why is it that the reaction is just like the synthesis, the decomposition, combustion, single and double replacement? Because this is this is the reason why all chemical reaction is now accompanied by the absorption and the releasing of your energy. So, whatever energy may be, there are basically two kinds. This is what I am talking to you a while ago. There are two kinds. Basically, there are two kinds. First is the kinetic energy associated with motion of an object, and its direction consequently are part of everyone's daily experience. So that is your kinetic energy. So your kinetic energy does have a formula of Ke Ke is equals to your mass times velocity over times velocity raised to 2 or velocity squared over 2. So problem example number 1 we have here. A rifle shoots a 4.25-gram bullet at a velocity of 965 meters second raised to negative 1. So what is its kinetic energy? So what is its kinetic energy? So you have here an additional information to you that a 1 joule would be now equals to 1 kilogram meter squared second negative 2. So that is now the conversion of your 1 joule. And then you have here the kinetic energy. You can take a screenshot of this one and we will go back again tomorrow. Okay? Okay. Next, we have the potential energy or the energy at rest. I have here an example, the ball pen. If the ball pen is not moving, meaning it does have potential energy. And the potential energy that this ball pen have, I cannot destroy it nor create it, but I could convert it to another form. Just like if I'm going to start moving this ball pen, so the potential energy is now being converted to kinetic energy. I didn't destroy, and also I didn't create the energy it has, but I converted it. Okay? Now, the potential energy is now being affected by the gravity. And your gravity does have a constant value of 9.8 meter per second raised to negative 2 or 9.8 meter per second squared. That is now the constant value of your gravity. And your potential energy or the PE does have a formula of mgh. That is the formula of your potential energy. So similarly, the potential energy of a particle having an electric charge Q depends on its location in an electrostatic field. And I do hope that you already know the electrostatic field so that it is not difficult for you to discuss this one. Okay? So that ends our topic for today. But we will summarize all. First, if we're talking about energy, there is now an involvement of your thermodynamics. And this thermodynamics, the first law is known as the law of conservation of energy, where energy cannot be created nor destroyed. And energy was always involved in chemical changes or reactions. And energy has two basic forms. You have the potential energy or the PE and the kinetic energy or the KE. Now, your PE is now given a formula of mgh, where m is your mass, g is your gravity, and h is your height, wherein your gravity is now be equivalent to 9.8 meter second negative 2. And last, your kinetic energy is now be equivalent to 1/2 mv squared. And this is stand for m is for your mass and your v is for your velocity. So this is now the summary of our lesson for today. So I'll be seeing you again